Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Welcome. This is Mr. Simon, and we are here to change our world using chemistry. So we are continuing with our lesson number 9. Our topic is still solutions and titration, and we are here to talk about iodometric titrations. Iodometric titrations. So, briefly, let's pass through what we covered last time. I had left you an example. We had not finished very well, and I know you got some of the answers. So we had stopped on part A, and we had been able to calculate the number of moles of sodium thiosulfate. So we are going to look through a simple how we calculated this question. So let's look through. So we have here, if you look at our answers, so like for example, part A of our question, our answer is 0.00007. And also we have part B, which was telling us to write the equation of reaction and identify the reducing agent. So that's the equation of reaction. You'll observe that actually the chloride ions are reduced to the chlorine aqueous is reduced to the chloride ions. So we also have this part C of our question, which is about to calculate the mass of our chlorine. So we first get the number of moles of, if you see very well, part C, we say 1 mole of iodine liberated 1 mole of chlorine from the equation here. Then after, the number of moles of iodine and the number of moles of the chlorine are the same. Then after we say mass is equal to number of moles here times molar mass. So we use the molar mass of chlorine, which is 35.5 times 2 times the number of moles of chlorine. Then we continue to part B of our question, which was telling us to show the disproportionation reaction of chlorine in the presence of water. So it disproportionates. So chlorine breaks down to give us chloride minus, and then also breaks down to give us chloride, the hypochlorite, where the chloride is actually positive 1. So who can define for us a disproportionation reaction? Actually, a disproportionation reaction is a reaction where we have both oxidation and reduction of the same chemical species. So if you look at our equation, you observe that chlorine is undergoing reduction in HCl and also undergoing oxidation in hypochlorous acid. So quickly, let's go back to our lesson today. We are going to continue with something similar. So we are going to determine the percentage of available chlorine in the bleaching powder. So the first part here, our question is in form of an experiment. We shall do it in the laboratory. It is quite exciting to do this experiment. So the first part is all about preparation of a solution. Preparation of a solution. Normally this is done by the teacher. So you prepare a solution by shaking. If it is, for example, jig, you get your jig and you dissolve it in in water. And then after you add distilled water up to 250 centimeter cubed mark. Then by this time we need, because it's a powder, we need to shake vigorously. We need to shake vigorously. So our experiment will start with shaking vigorously and then pipetting 25 centimeters tubed, then adding 20 centimeters of 2 molar sulfuric acid, and then add also potassium iodide. So when you have both of these things, that is, we have our original substance, then we have acid, we have also potassium iodide, they will give us iodine. So this iodine which has been produced will be then titrated with Fa2, which is actually sodium thiosulfate, using the starch what? Indicator. So we put the starch, then after we continue with our titration. So we have some theory here. So you'd observe, if you are looking at what we are doing, this calcium, this is our bleaching powder. It reacts with sulfuric acid or ethanoic what? Acid to give us the chlorine. Then chlorine, which is produced here, will react with the potassium iodide, and they will give us what? Iodine. So the iodine which is produced will be reacted with the sodium thiosulfate during the titration. So during this part, we shall have some specimen results. So we have our results. These are our results. They are similar. So we are going to be calculating, but before we calculate, let's try to get the average volume. Average what? Volume. Average volume. So we shall say, actually they are similar, but we can just say 25 as the working 0.6 plus 25.6 divide by 2. Then we shall get 25.6. That is our average volume. Then now we go to our question. The question is asking us, calculate the number of moles of available what? Chlorine in 250 centimeter cubed. So we are going to begin with actually our Fa2. Fa2, this is the volume of Fa2 centimeter cubed, which is Fa2, which is our sodium thiosulfate. So we begin and say number of moles of sodium thiosulfate. Sodium thiosulfate. We can say MV over 1,000. So this time we have 0.1, which is our molarity, times the volume, which is 25.6, divided by 1,000. So we shall get 2.56 times 10 to the power negative 3 moles. Yeah. Then from there we shall get the moles of what? Iodine. So before we go to the moles of iodine, we need to look at our equation. So we are going to use equation 3 and say, according to our, if you look at your screen, here we use equation what? 3. So we can say using equation 3. So we shall say actually it is a half. Half times 2.56 times 10 to the power negative what? 3. Negative 3. So we can use our calculator very quickly to get the answer. So we have 25.6. So you can use your calculator very quickly. So our answer will be 1.28 times 10 to the power negative what? 3. These are our moles. So we go to, if you look at the screen, we go and use now equation, yeah, we're going to use that equation. So using equation 2, then we get the moles of chlorine. So because mole ratio is 1:1, the moles of chlorine will also be equal to the moles of what? Iodine. So we shall say equal times negative 3 moles. So this chlorine which has been given out is what we are going to concentrate on. So from there we say that actually these moles are in 5 centimeter cubed. Then after we say 25 centimeter what? Cubed will contain of chlorine. Contains how many moles? 1.28 times 10 to the power negative 3 moles. And what about 250 centimeter cubed of chlorine again? Will contain 1.28 times 10 to the power negative 3 times what? 250 divided by 25. So our answer will be 1.28 times 10 to the power negative 2 moles in 250 centimeter cubed. So you see what we are having right now? So we have our first part of our question, which is the number of moles in what? 250. So now we are going to calculate the mass of available chlorine. The mass of available what? Chlorine. So if we have the moles, we say here that our mass will equal to number of moles times what? Molar mass. So the number of moles actually 1.28 times 10 to the power negative 2 times the molar mass of chlorine. Chlorine is normally 35, and because there are 2, we multiply times what? Times 2. So this is, we are doing part B of our question. So we say, so you can calculate as you help the teacher. So 7 times 1. So we shall have our answer. Who has got the answer? Okay, this is our answer. 88 what? Grams. So the last part, we hence calculate the percentage what? Percentage of available chlorine. So percentage of available what? Available chlorine. So as we have been calculating, when you are calculating percentage, things like percentage purity, we get the original, we get this one of the pure, divided by the original, which is 2.5. If you look at our original, our part of the question, just look at, you observe that initially we had 2.5. So we multiply times what? 100. So you calculate very quickly. So we have divided by 2.5. So our answer will be 36.352%. Yeah. So that is how we get our. So you can look at our procedure very well. That's how we get our percentage of available chlorine. If it was jig, we also do the same. So this experiment helps us in our daily lives. If you're working, for example, in the factory and you want to see if your bleaching powder, or for example, for example, where we have detergent, if it has, can we say detergent, or we can say bleaching powder has enough chlorine, or for example in water. If you have, for example, water, the water we normally use at home, if you want to know how much chlorine has been added, you can use the same procedure to make sure you test what you are doing. So we continue now. From there, we talk about the volume strength. The volume what? Strength. So now this time we are going to use iodometric titration to be able to get the volume strength of hydrogen peroxide. This hydrogen peroxide actually finds application. It finds application in very many parts of our lives, like for example, making of sanitizer, even in biology, or if you are someone who is selling chemicals and you want to prove or want to know how much, or you want to know the volume strength of your hydrogen what? Peroxide. You can use such a procedure or such an experiment or such calculation to be able to know how much, the volume strength of hydrogen what? Peroxide. Actually, the volume strength of hydrogen peroxide is a measure of how much oxygen, oxygen can be obtained from this hydrogen what? Peroxide. So the first part says determine the concentration determine the concentration of the stock solution of hydrogen peroxide. That's when we are going to do it. Then the second part, the volume strength of hydrogen what? Peroxide. So the question is that 10 centimeters cubed of a stock solution of hydrogen peroxide were diluted to 250 centimeter cubed in a volumetric flask. 25 centimeters of this diluted solution required after reaction. Excess potassium what? Iodide and the acid. As you see our equations, if you look at our equations very well. So we have the iodide, which is potassium iodide, the hydrogen peroxide, which is coming from the 10 centimeters cubed, and our acid, which is our acidifying what? Agent. So it will produce iodine, and the iodine produced will normally, as we have been doing in this iodometric titration, will now react with the sodium thiosulfate. Meaning when you are calculating, we are going to begin with sodium thio what? Sulfate. So quickly, let's go to our calculation. So we are now on finding volume strength. Finding volume what? Strength. So here we are going to begin with sodium thiosulfate again, the known volumes, which will be MV over 1,000. So what is our molarity? 0.1. What is the volume of sodium thiosulfate, which reacted 28, divided by what? 1,000. So we shall have 2.8 times 10 to the power negative 3. Then from there, we get the moles of what? Iodine. So we can write here, we can write and say using equation 2. What are the moles of iodine? We shall divide by 2, because 1 mole of iodine actually reacts with 2 moles of sodium thiosulfate from our equation. So we say times 2.8 times 10 to the power negative 3. Our answer will be 1.4 times 10 to the power negative what? 3 moles. So we have the moles. Then we go and then we try to find using equation 1. Now we go to equation what? 1. Then we try to find the number of moles of the peroxide. So from this equation, you'll observe that the hydrogen peroxide, if you look at your screen, 1 mole of hydrogen peroxide produces 1 mole of what? Iodine. So mole ratio is 1 to 1. So the moles of iodine will be equal to the moles of hydrogen what? Peroxide. So we have again 1.4 times 10 to the power negative 3 moles. So you see what we have. So from there now, we are going to say this one is in 25, like we had there. This is in 25. And what about 250? So we say 25 centimeter cubed of hydrogen peroxide will contain how many moles? 1.4 times 10 to the power negative 3 moles. Then what about 250 centimeter cubed of hydrogen what? Peroxide. It will contain 1.4 times 10 to the power negative 3 divided by 25 times 250 moles. Then from there, we have our answer as 1.4 times 10 to the power negative 2 moles in 250. But remember, this volume in 250, we actually used 10 centimeters cubed. We shall also say it means that this 10 centimeters cubed of hydrogen peroxide will also contain the same amount of what? Moles. Then what about 1,000? So we are going to change them to 1,000. Why? Because this molarity helps us to get the volume strength. So we shall have 1.4 times 10 to the power negative 2 times 100. Actually, it's 1,000 times 1,000. 1,000. Yep. Actually, I had put 10,000. Divide by 10. So we cancel like this. So our answer will be 1.4 molar. 1.4 what? Molar. Yeah. So I hope you followed, and this is how we get the concentration of part A. So we are going to go to part B, where we get the volume strength. They have not specified which volume strength, or at STP or at room temperature, but we shall say our volume strength. We can calculate both of them. Volume what? Strength at STP. We shall get it from this formula. We shall get it from that what? Formula, where we have 1.2 times what? Molarity. So we have 1.2 times 1.4, and we get our answer. Or volume strength at room what? Temperature will equal to 12 times what? Molarity. So we shall have 12 times what? 1.4. So you calculate and give us the answers very quickly. So that's what we have. So we are going to do like this. Answer. So 11.2. I'm going to check to see if your answers are correct. Actually, here we have 15.68 volume by volume. Then here is volume strength. So here we shall have 12 times 1.4. So our volume strength will be 16.8. Yeah. So the difference is because of the difference in our constants. The difference in our constants. The difference in our. So you can follow and see what we have done. See what we have what? Done. So that's how you can get your volume strength. If you're working, for example, in a laboratory, or you're working, for example, in a shop which sells these chemicals, you can prove. You can what? Prove. So because we are ending our topic today, actually it has been long, all from acid-base titration up to iodometric what? Titration. So we have some sample questions here. Like, for example, this exercise number 1, which is saying that the following experimental method in the laboratory was used in the laboratory to determine the percentage of copper in the sample of impure copper metal. Nitric acid was added to the sample of impure copper metal. So you observe this nitric acid, when it is added to copper, it changes the copper to copper 2. So then copper 2 now is reacted with excess potassium iodide, as you see in our equation. So you see this equation number 1, you observe that copper is reacting with the excess iodine. That's why we called it a back titration. Excess what? Iodine. So the iodine produced, if you recognize here, the iodine produced here was reacted with the sodium thiosulfate. Sodium thiosulfate. So after the reaction, they have said that the volume of sodium thiosulfate was 23.7 centimeters cubed. So the first question is asking us to calculate the number of moles of sodium thiosulfate. I think you can do this. Moles, we have done it very many times. Use our molarity. Then deduce the number of moles of copper in copper what? Nitrate. Then the mass of copper is given there. Then they are telling us to calculate the percentage of copper in the impure copper. So you can, we use both of our equations as we have done here. The first part here, what you do, you get the moles of sodium thiosulfate, get the moles of iodine, then when you reach here using equation 1, get the moles of copper. After getting the moles of copper, here we don't have, we stop here. After getting the moles of copper, we don't include this part because we don't have what? We don't have these big volumes. So from here, we quickly go, like we have done here. We quickly go and we find the mass. So somewhere after getting the moles of copper, we find the mass, then after divide by that mass of the impure sample. But part D is telling us to give the oxidation number and the electron configuration of copper in the copper 1 iodide. So the oxidation number of copper, we can maybe, because it is our last part of our lesson, we can just make a small illustration here. Let me try to use blue chalk and you can see it very well. So you'll observe that copper, the oxidation state of copper in copper 1 iodide is actually positive what? 1. So it means we have copper what? 1. So how do you write the electron configuration of copper in copper 1? So we first write the electron configuration of copper, which is 1s2, 2s what? 2p6, 3s2, 3p6, 3p6, then we go to 4s what? 2 and 3d. So normally copper we do like this. We make this one 10 and we make this one. We make this one 1. So we can check. We have 1, 2, 3, 4 is 10, 11, 12, 13, 19, that's 20 what? 9. So when you are removing electrons, copper 1, you say 1s2, 2s2, 2p6, 3s2, 3p6. We remove from here the outermost orbital. So you observe that copper 1 that's the electron configuration. Yeah. Thank you very much for following me today. Hope you followed our lesson. We shall meet next time. God bless you very much.